Product of vectors. Scalar product or otherwise called the dot product of two vectors. If A vector is a non-zero vector and B vector is another non-zero vector, theta is the angle between both the vectors, then the dot product is given by A vector dot B vector is equal to mod A vector mod B vector into cos theta. The projection of A vector on B vector, on vector comes in the denominator. So A vector dot B vector by mod of B vector is denoted by B cap. So that gives us A vector dot B cap. We know the unit vector B cap is nothing but is equal to B vector by modulus of B vector. So we have substituted B by mod of B is equal to B cap. And similarly, B vector on vector comes in the denominator A dot B vector by mod of A vector. So A vector dot A vector by mod of A vector leads us to A cap dot B vector. Next, moving on to the properties of scalar product. The scalar product of two vectors is commutative. A vector dot B vector can be written as B vector dot A vector. Scalar product of collinear vectors. Two vectors A vector and B vector are collinear. A vector, B vector both are on the same direction. Then the angle theta will be is equal to 0. Therefore, we know cos 0 is 1. A vector dot B vector will be is equal to mod of A vector mod of B vector cos 0 is 1, which leads us to modulus of A vector and modulus of B vector is nothing but the magnitude value, which is equal to AB. If the two vectors are in the opposite direction, A vector on the right side and B vector, but both the vectors are collinear, then the angle between both the vectors will be is equal to 180 degree. Cos 180 cos pi is equal to minus 1. That gives us A dot B is equal to minus of AB. Mod of A mod of B is equal can be written as AB, the length. Sign of the dot product. If angle between both the vectors is acute, angle is less than 90 degree, A dot B is positive. Angle between the two vectors lies between 90 and 180. So it lies in the second quadrant. Then the cos is negative. Therefore, angle between both the vectors will be negative. If angle between two vectors is 90 degree, then the dot product is equal to 0. Important. Two vectors dot product is equal to 0 if A is perpendicular to B or B is perpendicular to A. And one more condition, and if any one of the vectors is a 0 vector, then the dot product is 0. Dot product of equal vectors A vector dot A vector will be is equal to A square. I dot I, J dot J, K dot K is equal to 1. What is this I, J and K? I vector is a unit vector along the x-axis and J vector is a unit vector along the y-axis and K vector or K cap is a unit vector along the z-axis. So when we take the unit vector I dot I, J dot J, dot product of the same unit vector is equal to 1. Dot product of the different unit vectors leads us to the result is equal to 0. If m is a scalar, a number, m into a vector dot b vector can be written as m into a vector dot b vector. Next gives us the distributive property a vector dot b plus c can be written as a vector dot b vector plus a vector dot c vector. Next a dot b a plus b the whole square. We know a dot a is equal to a square. Therefore a square plus dot product 2 times a vector dot b vector notation must be given here and plus b square modulus of b the whole square. We know that b vector dot b vector will be is equal to b square magnitude. Similarly, the formula for a minus b whole square is equal to a square minus 2a vector dot b vector plus b square. A plus b vector plus b vector dot a vector minus b vector is a square minus b square. In terms of components, we take the vectors. For example, a vector is equal to some a1. Instead of giving a number, we have denoted as a1 I cap plus a2 j cap plus a3 k cap. B vector is equal to b1 I cap, b2 j cap, b3 k cap. We know that I dot I gives us 1, j dot j gives us 1, k dot k gives us 1. Therefore, taking the dot product, it gives us a1 into b1 plus a2 b2 plus a3 into b3. This is the dot product in terms of components. Next, angle between both the vectors. We know the We know the dot product of two vectors A vector dot B vector is equal to mod of A vector mod of B vector into cos theta. We want cos theta here, therefore this terms brings to the left, so it becomes cos theta is equal to A vector dot B vector by mod of A vector mod of B vector, or theta is equal to cos inverse of A vector dot B vector by mod of A vector mod of B vector. Triangle inequality mod of A plus B is less than or equal to mod A vector plus mod B vector. Note some important results here. Area of the parallelogram with adjacent sides as A vector and B vector is given by mod of A vector cross B vector. If A vector and B vector are the adjacent sides of the parallelogram, then area is given by mod of A cross B. Area of a triangle is given by half of A vector cross B vector if A vector and B vector are the sides of the triangle. Area of the triangle can also be given as half of modulus of AB vector cross AC vector or half of BC vector cross BA vector, or half of modulus of CA vector cross CB vector. Another formula for finding the area of a parallelogram: if the diagonals are known, D1 and D2 are the diagonals, then area of the parallelogram can be given as half of mod of D1 vector cross D2 vector. Let us solve a problem. Alpha given, beta vector is given, then they are non-collinear. To find the value of lambda for which alpha and beta are collinear. Since alpha and beta are collinear, we can write alpha is equal to scalar times of beta. Alpha, we know the vector, that is lambda minus 2 into A vector plus B vector is equal to T times of 4 lambda minus 2 into A vector plus 3B vector. Now, comparing the coefficients of A vector, we get lambda minus 2 is equal to T times of 4 lambda minus 2. And comparing the coefficients of B vector, 1 is equal to 3t, or T is equal to 1 by 3. Now substituting T is equal to 1 by 3, lambda minus 2 is equal to 1 by 3 times of 4 lambda minus 2, which gives us 3 lambda minus 6 is equal to 4 lambda minus 2, or this gives 3 lambda minus 4 lambda is equal to 6 minus 2, which implies minus lambda is equal to 4, or lambda is equal to minus 4. Find the value of lambda. We have found that the value of lambda is equal to minus 4. The vector product or cross product, otherwise the skew product of two vectors, A vector, B vector, denoted by A cross B, defined as a vector whose magnitude is given by mod A vector, mod B vector, sine theta. Theta is the angle between the vectors where theta lies between 0 and pi, and it is denoted by, and this A cross B is perpendicular to both A vector and B vector, and this A vector cross B vector is denoted by mod A vector, mod B vector, sine theta n cap. A and B are any two vectors, and theta is the angle between both the vectors. Then this A cross B vector is a vector which is perpendicular to the plane of both A vector and B vector, and this n cap is a unit normal vector to the plane of both A vector and B vector, and this A vector, B vector and A cross B vector form a right-handed system. Moving on to the properties, vector product is non-commutative. But a scalar product, we saw that A vector dot B vector is equal to B vector dot A vector. Scalar product is commutative, but the vector product is non-commutative. A cross B is not equal to B cross A, but A cross B can be written as minus of B cross A. Vector product of collinear or parallel vectors. If A vector and B vector are collinear or parallel to B vector, then the cross product is equal to 0. Cross product of two equal vectors will be is equal to 0. Cross product of the same unit vectors gives us 0 here. But dot product I dot I, j dot j, k dot k we saw is equal to 1 in case of the dot product, where cross product of the same unit vectors will be 0. and the cross product of the unit vectors taken in the cyclic order. J, when we reverse the direction, we give a minus sign. J cross I will be is equal to minus K cross J will be is equal to minus I, and I cross K will be is equal to minus J. Next, moving on to M is a scalar. If M is a number, M into A vector cross B vector can be written as M into A cross B or A cross M into B. Then the distributive property A cross B plus C can be written as A cross B plus A cross C. In terms of components, the cross product of two vectors is given in determinant form where the first row takes the place of I cap, J cap, K cap, and A1, A2, A3 takes the place the second row with the components of A vector, the coefficients of I, J, K written in the second row, coefficients of B vector written in the last row. Expanding the determinant, we get the value of A cross B. Angle between the two vectors is given by mod of A vector cross B vector by mod A vector mod B vector into sine theta n cap. So when we take the mod here, modulus of A vector cross B vector, we know is equal to mod A vector mod B vector into sine theta. N cap is a unit vector, so becomes 1. So from this we want sine theta. Taking the terms to the left, we get this is equal to theta is equal to sine inverse of A mod of A vector cross B vector by mod A vector mod B vector. Unit vector which is perpendicular to the plane of both A vector is given, B vector is given, mod of C minus A given, mod of A cross B cross C is given. Find the angle between C vector, A cross B vector is 30 degree, then A dot C is equal to. So we know that modulus of A vector cross B vector cross C vector is equal to 3. A vector cross B vector will be is equal to A vector cross B vector is given in the form of determinants which is equal to I cap into 0 plus 2. So that is I cap to 2 I cap minus 2 J cap plus K cap. We know A cross B here. Now mod of A cross B will be is equal to modulus of A vector cross B vector will be is equal to root of 2 squared plus of minus 2 whole square plus 1 square root of 9 which is equal to 3. But given in the question that mod of C minus A is 3 and A vector is equal to 2I plus J minus 2K. So mod of A vector will be is equal to root of again 2 squared plus 1 square plus minus 2 the whole square again root of 9 is equal to 3. So here mod of A vector is equal to 3 which is equal to mod of A vector cross B vector. Now from the question to 3. Now we know that definition for cross product of two vectors. This is we take this as one vector and C as another vector. So modulus of A vector cross B vector, modulus of C vector into sine theta. Theta is the angle between both the vectors given in the question, which is equal to 30 degree, which is equal to 3. Mod of A cross B we know is equal to 3. So 3 into modulus of C vector sine 30 is 1 by 2 is equal to 3. So we get which implies modulus of C vector is equal to 2. Now modulus of C vector minus A vector is given to be is equal to 3. So squaring on both the sides C vector minus A vector whole square is equal to 3 square which implies C square modulus of C square is C square plus A square minus 2 into C vector dot A vector is equal to 9. Now C square C is 2 so C square is 4. A mod of A we have found which is equal to 3. Mod of A is equal to 3. So 3 square is 9 minus 2 times of C vector dot A vector is equal to 9, which gives us 4 is equal to 2 times of C vector dot A vector, which implies C vector dot A vector is equal to 2. Question is to find the value of C vector dot A vector. C vector dot A vector is same as A vector dot C vector since we know that dot product is commutative. Therefore, it can also be written as A vector dot C vector is equal to 2. Moving on to scalar triple product, A, B, C are any three vectors, coplanar vectors. Coplanar lie on the same plane. Then the scalar triple product is given by A vector cross B vector dot C vector. One cross and one dot between the vectors gives us the scalar triple product. The scalar triple product leads us to finding the volume of a parallelepiped. We see a cuboid here, parallelepiped here. The base area is in the form, this is the base area in the form of a parallelogram. So height of the, when we draw a perpendicular from C to L, this is the perpendicular from C to L on the base. Here, this CL is considered to be the height of the parallelepiped. These two angles, this line A cross B vector and the CL are parallel. Since these two are parallel here, the angle between these two vectors are same, and therefore height of the parallelepiped phi, then the height of the parallelepiped according to the diagram will be is equal to, from the triangle OCL, cos of phi will be is equal to, this base area is in the form of a parallelogram, therefore area of the parallelogram is given by mod of A cross B. Therefore our aim is to find what is A cross B dot C. Therefore A cross B dot C is given by dot product of two vectors is modulus of, we know that A vector dot B vector is one vector, A vector dot cross B vector, C vector into cos of the angle between both the vectors. This gives us the base area, and modulus of C cos phi gives us the height, which gives us the volume of the parallelepiped. Volume of the parallelepiped can be denoted as box product of A vector, B vector, C vector. Moving on to the properties of scalar triple product, A dot B cross C can be written as A cross B dot C or C cross A dot B. Written in the cyclic order, the values does not change. That is A vector, B vector, C vector. Box product is same as, that is equal to, here also A vector, B vector, C vector can also be written as C vector, A vector, B vector. Cyclic order, the value doesn't change. If the order is changed, AB is written as BA, then we give a minus sign, since we know that A cross B can be written as is equal to minus of B cross A. Next, the scalar triple product is zero if any two vectors are equal. For example, box product of A vector, B vector, C vector becomes is equal to zero if A vector, B vector are equal, or B vector or C vector is equal. Any two vectors in the box product is zero, then the given scalar triple product is zero. Or if one vector is equal to scalar times of the other vector, for example, we have taken here, so the two vectors are equal, therefore the box product becomes zero, triple product becomes zero. Triple product is zero, in other words, if the two vectors are parallel or collinear. Any two vectors are parallel, we know the property that A vector cross A vector will be is equal to zero. So we say that if two vectors are parallel or collinear, then the triple product is zero. In terms of components, A vector, B vector, and C vector are written in terms of components as A1 I cap, A2 J cap, A3 K cap. Similarly, B vector and C vector. Then the triple product or the box product of A vector, B vector, and C vector can be written in the form of a determinant, and expanding the determinant, we get the value of A cross B plus B, A cross B dot C, or it can be written as A dot B cross C. Next question. Taking the cross product of these two vectors, A vector plus B vector cross B vector plus C vector dot C vector plus A vector. Now using the distributive property, this can be written as, this is equal to, we expand inside the bracket, we get A cross B plus A cross C, next plus B cross B plus B cross C dot C vector plus A vector. Now we know that B cross B is equal to 0. Now taking the dot here with C vector plus A vector, which gives us, this is equal to A cross B, taking this vector dot C vector, A cross B dot C, next one plus A cross B dot A plus A cross C. I take the next vector A cross C dot C plus A cross C dot A plus this term has become 0 here. Next, taking this term, B cross C dot C plus B cross C. This is 0, 2 times of C vector. This is also equal to 0. 2 times of A vector is equal to 0. Now we are left out only with A cross B dot C, that is nothing but box of ABC, written and given in the cyclic order, plus BCA is also in cyclic order, that is ABC. Now this gives us, this is equal to 2 times box product of A vector, B vector, C vector. Here x dot A, x dot B, x dot C is equal to 0. Show that A, B, C are coplanar. From the question, the dot products of the given vectors are 0. So it is known that x vector is perpendicular to A vector, B vector and C vector. That is, x vector is perpendicular to A vector and B vector. From the definition of cross product, if A vector and B vector are any two vectors, then in the plane of A vector and B vector, this A cross B vector is a vector which is perpendicular to the plane of A vector B vector. N is a normal vector n cap. According to this question, the normal vector is x vector. So we see that this x vector and this A cross B both are parallel. Both are perpendicular to the plane of A and B, and so they are parallel to each other. So I can write here that x vector will be is equal to some scalar times of A vector cross B vector. Lambda is a scalar here. Now this x dot C is equal to 0 implies this lambda times of A vector cross B vector dot C vector is equal to 0. I have substituted the value for x here. So dot is equal to 0. Now this is nothing but A vector cross B vector dot C vector. We know that is lambda times of box product A vector B vector C vector is equal to 0, which implies box product of A vector B vector C vector is equal to 0. This is then the box product is equal to 0. Hence we have shown that the given vectors are coplanar. Four vectors. The easiest way to remember the formula is A cross B cross C cross D. So it can be taken as A B D into C minus A B C into D. Or otherwise, the next formula it can also be written as A C D into B minus B C D into A. So one question following this vector product. Box product, we know it can be written as A vector cross B vector, one vector cross the next vector B vector cross C vector dot C vector cross A vector. Now we use the vector product of four vectors here. It can be written as this is equal to box product of A vector. I take this bracket here, A vector, B vector, C vector into B vector minus B vector, B vector, C vector, B vector, B vector, C vector into A vector. Now this vector is written as it is, dot C vector cross A vector. Now we know that two vectors are equal inside the box product and therefore the value is equal to 0. Now again this gives me this is equal to box product of A vector, B vector, C vector into B vector. This is dot C vector cross A vector. This is nothing but equal to 1 cross and dot between the vectors here combining. This is equal to box product of A vector, B vector, C vector into box product of B vector, C vector, A vector. It is in cyclic order. Therefore, it can be written as A vector, B vector, C vector, the whole square. Scalar product of four vectors. A vector cross B vector dot C vector cross D vector. So the first row is A vector dot C vector, A vector dot D vector. The second row will be b vector dot c vector, b vector dot d vector. Expanding this determinant, we get a scalar value. So it is called as the scalar product of four vectors. If A and B are any two vectors, then mod of A cross B whole square plus A dot B whole square. So we know the definition for A vector cross B vector, which is equal to mod of A vector mod of B vector into sine theta n cap unit vector. Taking the magnitude A cross B is equal to mod of A vector mod of B vector into sine theta mod of n cap is equal to 1, we know. Squaring here, mod of A cap cross B cap, B vector cross A vector will be is equal to modulus of A vector square modulus of B vector square into sine square theta. So this is one value. Next, we want to find what is A dot B. A vector dot B vector the whole squared. According to the definition, we know it is equal to modulus of A vector square modulus of B vector square into cos square theta. Now, this is equation number 2. So, adding 1 and 2, we get mod of A cross B whole squared plus A dot B the whole squared will be is equal to adding these two values. Mod of A square B square is common, taking out modulus of A vector squared, modulus of B vector squared. Then we get sine square theta plus cos square theta. So that is equal to 1. Sine square theta plus cos square theta is equal to 1. So the value will be mod of A square is nothing. Mod of A vector square is A square. Mod of B vector square is B squared. Or it can be written as mod of A vector square into mod. The next question. A vector given, B vector is given, C vector given, three vectors such that the projection of B vector on A vector is A vector, A plus B is perpendicular to C, and then B is equal to. So, projection of B on A, B vector on A vector is A vector, which is equal to B vector dot A vector divided by modulus of A vector will be is equal to modulus of A vector. So which gives us this is equal to B dot A, taking the dot product of A vector and B vector. So this is the A vector and the B vector taking the dot product. 1 into B1 is B1. I dot I is 1. Coefficient of J is 1. Coefficient of J in B vector is 2. So 1 into B2 is B2 plus root 2 into 2, root 2 into root 2 is 2 whole divided by 2 is equal to modulus of A vector will be root of 4 which is equal to 2. So right hand side is equal to 2. So we get B1 plus B2 is equal to 4 minus 2 is equal to 2. So this is the first equation. Next equation from the question A dot B is perpendicular to C. So A vector plus B vector dot C vector is equal to 0 since A plus B is perpendicular to C. So that is A dot C plus B dot C is equal to 0. So taking the dot product of A vector and C vector. So here A vector is 8. 8 plus 5b1 plus b2 plus 2 is equal to 0. So this is equation number 1, equation number 2. Now from 1 and 2, solving both the equations, we get the equations from 1 and 2, we get b1 is equal to minus 3 and b2 is equal to 5. Now substituting the value of b1 and b2 in our b equation, we get B vector will be is equal to minus 3 I cap plus 5 j cap plus root 2 into k cap. Now we want modulus of B vector. So modulus of B vector will be is equal to root of 9 plus 25 plus 2 which is equal to 6.